which is not usually the case. I frequently give talks elsewhere, but nobody's a prophet in his own land, so I don't frequently give talks in Barcelona. Anyway, today it's a pleasure to talk about the science and fiction of space travel. I only have 45 minutes to address that, meaning that, of course, I will only focus on a number of highlights, because 45 minutes, even if I use relativistic velocities in my talk, will not be enough to cover everything. Well, just to give you the basis, I don't know your background, probably everybody's familiar with that, but in any case, just let me go backwards in time to day in 1666, where a young Isaac Newton, 23 years old by then, was taking a break in the English countryside, and suddenly an apple fell from an apple tree. Well, usually a layman would just ignore the event, or maybe they would have wondered about how to make cider out of the apple. I don't know whether Newton liked cider or not, but then he ended up thinking about why the apple fell, and actually that gave rise to a number of laws, and in particular to the famous law of universal gravitation. Something I don't have time to cover is why Newton took 21 years to publish that he actually unveiled in 1666 and appeared for the first time in the famous mathematical principles of natural philosophy back in 1687. But anyway, the important thing, remember, I'm from academia, so forgive me for that, but I will show one formula during my whole talk today, so I hope nobody will suffer a heart attack. If you don't like formulas, just close your eyes for a second. I'm going to address just one concept that we need to understand in space travel, which is the concept of escape velocity. So this is the minimum speed that you require to actually escape from a gravitational pull from a planet, a moon, a star, a solar system, whatever, without further propulsion, okay? So you want to get rid of something, I don't know, this bottle of water, this speaker, for instance, you want to get rid of me, then at which speed do you need to throw me away just to avoid that I fell back and I continue with my talk, right? Well, the number can be evaluated here, and mainly it depends on the properties of the attractor, so the planet, in this case the Earth, so we should plug here the mass of the Earth and the radius of the Earth if you are planning to launch me from the surface, so you put here the radius of the Earth, and the number is probably familiar to most of you. This is 11 kilometers per second, okay? Sometimes journalists make me a very bad time just when they translate a text that I have written for the press or for the media, and then that goes to a stylish corrector or whatever, and then they decide to switch my kilometers per second to kilometers per hour, which of course is not the same. 11 kilometers per hour is the velocity that you will get if you rise to the other classroom here in this building, so you don't expect to escape the gravitational pull from the Earth in that particular case. Anyway, remember that number, we'll come up with that. With this minimum luggage, we are capable now of moving from the Earth to our closest neighbor, which is the moon, of course, something extensively revisited in the literature and cinema of science fiction. And just let me emphasize that during many years, the challenge here was to understand that the mechanisms that we used for an aircraft or for moving around in our planet, including the atmosphere, doesn't work in space, basically because the main distance between the Earth and the moon corresponds to void. Okay, so there's no air in that, and no matter whether Judith Merril in 1916, one of her novels, actually decided to send a number of colleagues and citizens to the moon using a helicopter. Okay, well, that probably wouldn't work because essentially in that region, region between the Earth and the moon, there is empty space. There's no air in there, and so a helicopter probably will not work. At least, well, you maybe will be able to move the helices and everything, but that would not have the expected effect described in the novel. Okay, just to give you a flavor. So we are here somehow, and probably you can see this thin bluish line there at the limit of the Earth. This is basically the size of the terrestrial atmosphere. So it's about 100 kilometers. So you could be optimistic somehow and say, well, an aircraft or a helicopter may work there, even a balloon. But again, just subtract 100 kilometers from there, that's nothing. Okay? So that means that most of the distance is empty space, so you need to understand that maybe you need another mechanism to attempt a space travel. Okay? And that was a troublesome thought that many people had early on during the 20th century. And just let me review what a scientist, a chemist actually, a British chemist, Alexander Bickerton, was claiming in 1926, okay, less than 100 years ago. So he actually considered the idea of shooting something to the moon as a foolish idea. And just let me go quickly through the text, okay? So he said, for a projectile entirely to escape the gravitation of the Earth, it needs a velocity of 7 miles a second, okay? That's basically the true number, 11 kilometers per second, okay? The thermal energy of a gram at this speed is 15,000 calories. So basically what he calculates is, okay, imagine that you have a tiny spaceship, it just has 1 gram of mass, okay? And I want to send that 1 gram of mass at the velocity of 1,000 kilometers per second to escape from the gravitational pull from the Earth, okay? What he would, well, the number that you need in terms of energy, that corresponds to 15,000 calories. Right? You catch that? Good. Well, the idea is that he said, well, the most violent explosive that was known by then was nitroglycerin, which provides 1,500 calories per gram. So even had the explosive nothing to carry, it has only 1/10 of the energy required to escape the Earth, and hence the proposition appears to be basically unsound. Okay? That's what Bickerton said. Today, in the 21st century, it's time to make one of these wonderful face palms that are so fashionable these days, okay? Because actually we can make a double face palm, because actually there are two mistakes in this argument, okay? So the two mistakes are the following. The first one is that, yeah, I mean, technology advances forward, and the idea is that today we need, we know substances with a larger explosive power than nitroglycerin. So you have to be careful when you actually claim that something is not possible based on technology, okay? So basic impossibilities appear at a more fundamental level, which is at the physical level, not at the technological level, that frequently can be overcome unless you violate any physical principle. And the second is that basically Bickerton is thinking on a shoot, burn-alike. I mean, like an instant shoot to the moon. You provide the spaceship with 11 kilometers per second at lunchtime, and then, yeah, this is not the idea. This is not the idea at which modern space travel, hopefully, is taking place. And the astronauts are happy about it. Okay, we'll see that in a second. Well, let's go back to the space shuttle, which was familiar probably to many of you. It was in operation until recently. And the idea is that when the countdown ends, and then there is the order for liftoff, basically the shuttle doesn't appear moving at 11 kilometers per second already, okay? Basically, it is at rest. There's a lot of, you hear the roar of the engines, you see a lot of smoke coming in, and then you can notice that the spaceship carries with it, fuel tanks that actually provide the key point for space travel. Okay? Actually, after continuous burning of fuel, 50 seconds after the engines have been have been activated, let's say, the space shuttle just gets 1 kilometer per second, so 10% of the required escape velocity, and it takes basically 9 minutes at the constant gravity, at constant acceleration of about 3 times the Earth gravitational value, let's say the surface value, to achieve escape velocity. So the average time during which continuously we are actually burning fuel takes about 9 minutes, okay? And that's the key to progressively achieve escape velocity, rather than in a burner-like argument where you use a cannon to, send your astronauts to the moon. That takes place instantaneously, okay? And I stress here this number. This is basically what the astronauts may suffer inside of a spaceship, okay? That means that if you put an astronaut on scales to determine its weight, at the time during launch, basically its weight may have increased by a factor of 3. Okay? So if you're I don't make any number to avoid any conflict with any of you, okay? But let's say a human that has a weight of, say, 70 kilograms, if during launch, will dramatically look at the scales and we'll see that its weight, apparent weight, has increased to 210, okay? But again, this is uncomfortable, but again, no risk at all, and we'll see that in a moment. So we know, thanks to the early days of manned space travel and also high-speed airplane knowledge and so on, that the effect of gravity acceleration on astronauts is a little bit annoying, okay, to put it in plain words. At 3 times the Earth's gravity, which again is not an extraordinary acceleration, this is a complicated thing because basically this depends on a number of factors and in particular on the orientation of the astronaut with respect to the axis of acceleration. So take these numbers as approximate. These are not, you know, like something that is mathematically proven in the sense that, again, you can change your direction with respect to acceleration and some of these numbers may vary a little bit, okay? But the idea is that the blood that circulates through our veins and so on basically tends to accumulate under some extreme acceleration at given spots in our body, okay? And in particular, this accumulation translates into a reduction of the blood pressure at certain places in the body, in particular at the retina, where an astronaut at 3 Gs, for instance, during the space shuttle launch, can lose temporarily vision, okay? Well, that's not a big deal. I mean, if you are comfortably seated inside of the space shuttle, if you lose vision for a while, well, I mean, you are not there for holidays. That's your work, right? So anyway, but that's, again, this ends up in 9 minutes. So in 9 minutes, you will recover your vision, no problem, okay? However, if you are piloting, for instance, a supersonic military aircraft, okay, and you make a sudden turn, okay, and then you are suffering an acceleration of 3 Gs or more, then your temporary vision loss will be something that could become immediately permanent in case that you collide with a mountain or something that you have not anticipated in your viewport, okay? So careful about that. Again, depending on the context, the effects can be dramatically different, okay? At 6 Gs, think about it, we are not talking about 100 Gs or something like that, just 6 times the gravitational value of the Earth surface gravity, let's say. The reduction of this blood pressure affects the brain. The brain gets the privet of oxygen, and then you know that the brain without oxygen doesn't work well, and in a matter of a minute, you lose consciousness, and that could could actually become deadly in case that this acceleration phase takes long enough for the brain to be deprived of oxygen, okay, for more than a minute. That occurs for all humans except for Bruce Willis. Okay? We'll see that in a moment. Bruce Willis apparently it's next door to a superhero somehow because he can go beyond that limit. Anyway, the question is that probably you have seen Armageddon. Armageddon is a wonderful movie. NASA actually uses Armageddon in his management training program to actually ask the participants to identify mistakes by watching the movie. Okay, and the last time I checked that from the NASA webpage, they have identified 168 impossible things occurring in Armageddon. 168 things, okay? Well, to make a long story short, actually there is an asteroid, approaching the Earth. You know, this is a real menace. We have nice examples of asteroids that have collided with the Earth. You know that 65 million years ago, probably the fall of an asteroid of a few kilometers actually provided such a weather change that eradicated dinosaurs as the dominant species on Earth, and thanks to that we are here. Okay? Anyway, in more recent times, 50,000 years ago, a nice rock which was just 50 meters in size, it's important that 50 meters inside, created a crater that you can visit in Arizona. It's a very interesting activity to do. Created a crater, a 50 meters rock created a crater 1.2 kilometers wide, okay, and 175 meters deep. Okay? The reason why there is this mismatch between the size of the impactor and the crater itself is because, I mean, the incredible energy that the rock has when it falls and touches ground vaporizes basically all the area around of the original rock, okay? And then you can actually imagine the effect that, as anticipated by Armageddon, what would happen if an asteroid the size of Texas, so 1,000 kilometers, actually collides with the Earth? I mean, come on. I'm not in a good mood to describe that on a Saturday morning, so I will skip the details. Just let me mention something, okay? So, how many, I mean, is this a real menace? So we have, are there so many asteroids that big around the Earth? Well, we calculate that objects larger than 100 meters, which is considered as the threshold for having a real effect if a rock falls on Earth, are estimated to be about 25 million asteroids bigger than 100 meters orbiting in the solar system. Out of them, we have cataloged about 300,000 asteroids. Okay? Again, I mean, you say, oh, why don't we catalog everything? Well, ask your politicians to devote more money to science. Maybe then we will be able to do that. But since, again, this is a long-term menace, probably in 4 years' time, no asteroid is going to fall. Who cares? I mean, maybe the next president will decide to do something. You know how it works. Anyway, the idea is, how many asteroids that big have we cataloged among these 300,000 asteroids that we have orbiting in the solar system? Well, the answer is just one, Ceres, which has a size of about 950 kilometers. So, I mean, come on, what are the astronomers in the movie doing? I mean, they have missed the second or the first largest object in the solar system, aside from moons and planets. So we know 300,000, and the goal is to catalog everything down to 100 meters, and then by accident, we missed one that is 1,000 kilometers wide, okay? I mean, astronomer life is a mess. You don't know that. Anyway, the question is that, yeah, well, hopefully Bruce Willis is around. He's not an astronaut, that's a long story. He's recruited from an oil platform, you know, one of these platforms that you have in the seaside, where actually they dig and using big drills to actually extract petrol from oil from underground. And then, well, he goes there. Well, the description of the asteroid is just, I mean, it's just hilarious, okay? So this is a nickel, this is of the class of nickel iron asteroid, so it's extremely dense thing, okay? I would love to have the drills that they use in the movie to actually make a hole 200 meters deep into a nickel iron substance for home applications. I would do that. I would love to have that. And then what the heck is doing these sort of crystal structures in a nickel iron asteroid is something I cannot answer. Anyway, the thing is that the idea is put a bomb, go away before it explodes, and then cross your fingers, right? So well, the idea is that from control mission, they say, the astronauts, well, when do you deploy the engine, the nuclear engine, you will have to accelerate at 9.5 gravities during 11 minutes. It's time to pray, indeed. Okay, it's only a miracle will make you survive if you are planning to accelerate during 11 minutes at 9.5 Gs. Remember that 6 Gs are deadly for 1-2 minutes. So yeah, well, maybe it's Bruce Willis. I mean, come on, we are used to that. Anyway, then what happens at the other side of the pond? I mean, yeah, we have considered the effects of large gravity. What about the effects of small gravity? Well, there are a number of them. Just let me, because I'm running out of time as usual, just let me skip some of them and focus in the particular ones. There is one that you can actually test at home, okay? The idea that in the absence of gravity, or in microgravity conditions, you know, our bodies actually structure in terms of a column with vertebrae that are mobile somehow, okay? And the idea is that when you don't act any force on your body, these vertebrae tend to relax, okay? So they don't have the same function as when we are just moving around in the earth, and when we have a heavy backpack, or we are, I don't know, working in different jobs where we have to carry on our shoulders very heavy stuff, right? So the idea is that basically these vertebrae relax in microgravity conditions, and basically we grow, within quotes, about 5 centimeters, okay? So actually, if you sleep horizontally, well, a wonderful night, I would love to sleep like that for 8 hours or so one day, then the idea is that you wake up in the morning and you are taller by 1 centimeter, that if you perform the same measurement by night, okay? It's between 1 and 2 centimeters, and then you can test that at home. It works, okay? Then in space, of course, after several days being there without any gravity around, the effect amplifies somehow, and then you reach these 5 centimeters. Unfortunately, if you're planning for space travel just to grow a little bit, as soon as you go back to Earth and spend a couple of weeks here, then your size returns to the normal number, unfortunately. Okay? Aside from this funny feature, all the other things are really effects that are not good. We don't know the long-term effects, but at the short term, the maximum that a person has spent in weightlessness condition is 1 year, so we don't know what will happen in 10-year time or 20-year time. The idea is that for reasons that we don't know, but we know that they occur, our bones in weightlessness or in microgravity conditions lose minerals, calcium in particular, and this produces what is called the spaceflight osteopenia, similar to the process that elder people on Earth suffer, and then that's the reason why elder people, when somebody falls, an elder people has a larger probability of breaking a leg, for instance, than a kid. Okay? Simply because osteopenia is also a frequent effect of elder people, and that calcium decreases the strength of a bone. Okay? So why is this occurring to astronauts? We don't know, but we know that this occurs. There are alterations in the cardiovascular system. Recently, I was reading some stuff on that, and I read that basically the larger exposition to a radiation field that astronauts suffer when they abandon, our homeland, let's say, are the reason why most of the astronauts have suffered incredible problems of in the cardiovascular system. So it's one of the side effects of being an astronaut, okay? You may suffer cardiovascular problems because of the effect of radiation. Okay? And there are experiments today being performed, of course, with rats and animals in the lab, which are accidentally, well, on purpose actually, bombarded with radiation to see whether these effects can be understood in a better framework. The most interesting syndrome somehow is the famous space sickness. That, careful, 50% of the astronauts suffer in space after training on Earth and everything. Astronauts suffer space sickness, 50% of them, in the first 3 days of permanence in space. Okay? Actually, NASA, there are some funny guys in there, they have coined units for this space sickness. You know that physicists like units, okay? We express things in units. So they have invented the Garn units to express your degree of adaptation to space. Okay? This is because a US senator some years ago, he's the record holder of having the worst adaptation to space ever. Okay? So apparently 1 Garn is that you will have such a bad time in space as the senator Jay Garn had in his time. And usually we humans, I don't know about Bruce Willis, but humans, we usually range between 0.2, 0.5 Garns normally, things like this. Okay? Then, if you are still thinking about going to space and becoming an astronaut, think about muscle atrophy, loss of body mass, sleep disturbance, excess flatulence. So if you combine the space sickness with excess flatulence, the aroma inside the spaceship must be funny, let's say. And long-term effects, still questionable, like brain deterioration, Alzheimer, and so on. Okay? There are very interesting movies and documentaries on how animals get used to space. My favorite is one spider that actually was carried inside the Skylab laboratory many years ago, who, of course, poor spider, nobody told her that she will be weightlessness, so then the spider decided, what, to build a web, right? So the spider jumps, but of course nobody tells you, oh, you don't have any weight, you will not fall where you expect. You will fall on the other side of the cabin, okay? And so the spider gets a little bit like having 2 gins and tonics and then, being disoriented or something. At some point, she recovered, and then she managed to create a space web, a spider web, as you can see here, with a reasonable shape. Anyway, yeah. Situations about that science fiction has illustrated to overcome these limitations of weightlessness are multiple. One of the early ones was the famous space station that appears in 2001. That's a little bit old-fashioned, so I said, okay, come on, bring something new today, otherwise people will think, come on, don't put an example of 69, okay, fine. In The Martian, there is a similar thing, okay? So there's a piece of this Hermes station where actually is spinning around the main symmetry axis, and because of the spin, we can imitate, never generate, but we can imitate the effects of gravity through an acceleration. Okay? So combining the size and the dimensions of that wheel and how fast it rotates, you can actually feel inside like in a similar way as you would feel when you walk around on Earth. Okay, so this is something that is well known, has been illustrated in many movies, probably the most recent one in The Martian. Speaking about The Martian, I took that because probably after the moon, Mars is the next frontier. Okay? Mars has been revisited extensively in literature, in science fiction movies as well. I will skip the comments on Barsoom. These are wonderful stories, old-fashioned, by Edgar Rice Burroughs, a very creative writer. There has been a movie recently about that, which is really, well, you have to look at that with, thinking on the time when the novels were written, because that doesn't make any sense today, okay? There is this guy, John Carter, who by accident gets transported somehow to Mars, and then because he's there and the gravity is different, he makes jumps like crazy, okay? Jumps like 100 meters tall or something like that. Come on, I mean, you just need to go to Wikipedia these days and calculate which is the change in gravity on Mars. The effect is less than a factor of 3, okay? And that means that if you jump, imagine that you want to jump without any impulse, so from rest like this, and you make you try to reach as high as you can. People with some good training, basketball players and so on, they can rise about 50 centimeters from the ground to the sole of the shoes. Let's say 50 centimeters, okay? The same person doing the same type of jump on Mars will reach 1.3 meters, which is a hell of a jump, okay? But again, come on, this is not 100 meters, okay? So we are off by, let's say, a big factor between what the movie is telling and what reality is. The problem is that this thing happens in Mars. If somebody would tell you this is a different planet, we don't know its name, I would not be here just criticizing that. Okay? But as soon as you put Mars, come on, Mars has some size, some mass, some gravity, and then you have to be respectful with the laws of physics. Okay? Well, I will not mention that today we know that there is no liquid water on Mars, at least at the level of finding nice rivers and so on. We know there is water on Mars, and I bring you a proof. There is water on Mars everywhere. I mean, you can find this in Wikipedia. Okay? Good. Anyway, another movie that has described things that occur on Mars is the wonderful Total Recall, okay? Where some astronauts by the end of this century have partially terraformed already Mars. And here there are a number of things I also will not elaborate. Remember that one of the astronauts gets accidentally exposed to the vacuum of the tiny pressure and the tiny atmosphere that is on Mars, 7 millibars only, and then it almost explodes, right? Well, I mean, humans will die for sure if you are exposed to vacuum, let's say, and that's enough, okay? You don't need to explode, okay? So actually we don't explode, okay? So the accidents that have occurred to astronauts, and we know for sure that this doesn't occur, okay? Now, if you want to learn more about terraforming, which is a very interesting way to actually rebuild the properties of a foreign land and to accommodate them to our human interest, there's a lot of ethical debate behind, as you can imagine. There is this wonderful the trilogy from Kim Stanley Robinson that almost depicts terraforming Mars as if it would be real, okay? It's a wonderful reading, and you will learn a lot about the different techniques proposed and some of the ideas that lay behind the possibility of terraforming in the future some of these planets around the Earth. The only problem is frequently the time scales, okay? And then, if you look back to Total Recall, there is a funny thing. Sorry for the spoiler, because I'm going to talk about the end of Total Recall if you have not seen it, but at the end, suddenly there is some project to actually melt an incredible amount of underground iced water, okay? And that saves the life of Arnold Schwarzenegger, because then as soon as this water gets melted, you generate a wonderful atmosphere on Mars, and then he can safely breathe. But come on, do we breathe water vapor or what? Okay. Maybe that day I was not in class when my teacher was telling that, but I thought that we were breathing nitrogen mostly, and then some oxygen and some other stuff. If you just melt water ice, you will get water vapor, I think, right? So there's something wrong in that. So careful about just thinking that you can just melt some ice and that would become, you can generate an atmosphere. That's one of the ideas beside the project, the real project of terraforming. The main issue is how to make it breathable for humans, okay? That's a different story. And that's the bottleneck of terraforming. People speculate that probably you will need 10 to the 5 years, not just the breath of Schwarzenegger. Maybe since he's very, very big, maybe he's a little bit small, okay? A little bit slow in his actions, but I doubt that he takes 10 to the 5 years just to breathe and wait until the different plants and everything has transformed the atmosphere into something breathable. Anyway, So back to The Martian. The Martian has been translated here. I mean, here we always have the difficulty in Spain that when there is a movie from the US, we always have to learn the original title and the translation that sometimes deviates deeply from the original, okay? In this case, The Martian was translated as Marte, Mars, okay? Why? I mean, is it so difficult to translate that for El Marciano, which would be the equivalent to the Martian? Maybe because there was some jokes expected after writing El Marciano, for instance, this one. I don't know. Maybe that's the reason why, okay? But in any case, for those that are not familiar with the gentleman, we have the version across overseas, which is this one, okay? Anyway, good. So, back to The Martian. The idea is that, I remember I was in the movies, watching that movie for a while. I mean, I have not been in the movies for a number of months for a number of reasons. And so I was with my wife watching the movie, and then the movie starts, and there is, probably you have seen that. So I will just reveal the early stage. I will not spoil it totally in case you want to watch it and you have not done it yet. Well, the idea is that there is a heavy dust storm covering the whole planet, and then that creates some sort of a hurricane at the level that Matt Damon gets injured after that, and he gets abandoned. The rest of the crew believes that he's dead, and so they leave. It was impossible for they to stay there. So I was in my seat in the movie theater thinking, come on, what's the pressure of Mars? It's 7 millibars. How can you expect to create a hurricane in an atmosphere that is so tiny? And the reason is not, you cannot, okay? So yeah, you can perform, you can have nice features related with dust and wind in Mars. You have global events where the whole planet gets covered in sand and so on. But again, the maximum that you would expect is some sort of gentle breeze moving around you, which is annoying because you will have some dust and so on, but you will not be jammed to the other side, of your land because of a hurricane or things like that. Okay? So that's the best thing of the beginning of Mars. The second problem related with Mars exploration is what may happen to a person that spends 2 years on Mars or something like this, okay? Or for whatever the purpose, a person that is actually embarked in one of these fashionable trips to Mars that everybody's advertising. Oh, we'll go to Mars in 10 years or in 15 years or in 20 years. Is it a safe thing to do? The answer is no. Okay? The answer is no, because basically we have to remember two things, okay? Forgetting about the possibility of a solar storm during the space trip that can actually, increase the radiation inside the spacecraft dramatically, okay? There is a secondary effect which is very important. On the surface of Mars, there is essentially no magnetic field, okay? Magnetic field actually protects us, shields us from the arrival of charged particles. Actually, there are two belts surrounding the Earth, the Van Allen belts, that actually trap some of these charged particles and prevent them to reaching ground level, and we are safe from that, okay? Thanks to the magnetic field on Earth. On Mars, there is no analogous to that. And second one, because the atmosphere is so tiny, there is no ozone layer in the atmosphere, so any high energy radiation that here is trapped because of the ozone on Mars will not act on you, will not shield you, okay, unless you immediately, as soon as you reach Mars, then you put yourself under a cave, made with lead or something big, several meters of lead or whatever. But again, who carries that? Space travel is expensive, so it's not as easy as it may look like. So something to consider. I had the chance to talk with some of the responsibles of the manned missions in ESA, in the European Space Agency, and everybody's aware of that. The funny thing is that this is not frequently seen in the media. I have seen some reports somewhere, but this is not frequently advertised when people launch these wonderful programs of, okay, why don't we go to Mars one of these days, okay? Spend your holidays in Mars, or things like that, okay? So careful about it. Good. Okay, I have like 10 minutes, so let's see whether we can go beyond the solar system, because the solar system at some point gets even boring, right? Planets, essentially there's no water, whatever the movie says, who cares? But the reality is that we don't know any civilization somewhere. So let's see whether we can go to some interesting planets, and science fiction is a gold mine for some of these interesting planets. One of the very interesting planets is Mesclin, that has been visited by science fiction. Hal Clement told us about it basically 60 years ago or so, when he imagined a world that has a gravity at its poles that takes a value of 700 gravities, 700 Gs. Probably even Bruce Willis will not survive there, okay? But then the planet spins so fast that in the equator, the value is reduced by centrifugal forces to 3 Gs, okay? That's interesting because at 3 Gs, I mean, the guy was clever. At 3 Gs, a human may have some vision problems, but a human would survive. So it's a very interesting thing, okay? Of course, he thinks about that the creatures in such a planet will be totally different. He thinks about flat structure rather than tall, because again, you know, if you think about any type of pump that has to work in a world with 700 Gs, that would be a technological challenge, okay? So it's much better to pump things horizontally. So he imagined a society made of creatures that are flat, and I don't have time to elaborate here, but this tells you a lot about how a society evolved under such huge gravities would differ from us. Okay? And I just put you an example. Archery, which is an activity that has been developed by humans everywhere, okay? Well, archery would be an extreme sport in Mesclin, okay? Why? Because if you throw an arrow from the height of a mesclinite from 5 centimeters at 700 Gs at a typical velocity of 50 meters per second, that's the typical velocity of an arrow, it will fall 30 centimeters, the arrow will make like this. Okay, archery, that would be archery, okay? So, if you are not careful, if you measure 40 centimeters in length, you can end up with the arrow on yourself, okay? So, careful, because using archery can kill you. It would be extreme sport in Mesclin, okay? Anyway. Good, other worlds of unbearable gravities. Life in neutron stars, anticipated by Larry Niven in his short novel, which actually was published 1 year before the real discovery of neutron stars in the universe. Okay? And then the duo of novels from Robert Forward. And more recently, Interstellar, okay? Which, thanks to the great scientific advisor, Kip Thorne, which will be likely visiting Barcelona in May, okay? He anticipated a plot in which wormholes, black holes, worlds of extreme gravity at least some of them we think are there in the universe, can actually appear in a well-treated way in a movie, okay? And in particular, he speculates about a planet, Miller's planet, that orbits a giant black hole, and where time doesn't work in the same way we are used to, okay? In particular, he exhibits, based on general relativity, the idea of time dilation due to gravity, and in particular, he illustrates that 1 hour on Miller's planet corresponds to 7 years on Earth, okay? Well, there are a number of applications that you can do in that context, okay? For instance, any of you lives in a penthouse, in a tall flat somewhere? Well, bad news for you, because actually, gravity slows down at the ground level and passes quicker at the top of the building. So you will live less. I know that penthouses are more expensive, but probably real estate investors don't know about general relativity, okay? So they ignore that time passes faster at the top of the building than on the ground. But of course, if you have a penthouse, come on, enjoy the view. Don't worry about that, because you will just live something like 1 femtosecond, less than expected if you would be living at the ground stage. Of course, the effects for a planet like Miller require the presence of a strong gravitational field. Earth's gravitational field is very weak, so we don't have to worry about that. Okay? Of course, to go to some of these planets of fiction, we need propulsion, we need spaceships, and again, in many movies, this has been treated differently. Okay? It's not enough to pilot a spaceship to just turn the steering wheel. Okay? It doesn't work like this. This works on a car, or this works in the framework of an aircraft in the atmosphere, where you can use the flaps and moving some pieces, some components of the wings of the plane to actually move around through friction. But in a space where you have vacuum, there is no friction possible, and then you have to rely on other things. You see these little jets here? Okay? So this is basically the way in which we move in space. You have a spaceship, and then based on something that physicists call momentum conservation, the idea is you throw something in one direction, and then by recoil effect, the rest of the spacecraft moves in the opposite direction. Okay? This is like if you are skating on ice, okay, and then you are stuck at the skate place, you don't know how to move. You start moving, but imagine that friction is really zero, which is not really, but imagine that. So you will start trying to move with your skates, zero effect. The only way to do is to do something a little bit nasty, okay? It's like, well, I will only describe one part, which is like to remove your clothes, throw it in one direction, then by recoil, you move in the opposite direction, okay? Other effects I'm not going to describe, other possibilities. Anyway, so this was seen in Gravity. This was seen before by Clint Eastwood in Space Cowboys. You can see here that the space shuttle had 44 exit holes or micro thrusters where basically, you can actually eject some gas there, and then the spaceship can move accordingly. Okay, so it's an interesting way of doing it. Imagine that thing. This is a real photograph of a NASA astronaut trying to move around without any cord, thanks to the backpack during these EVAs, extravehicular activities, in which basically he has the similar capability of moving around than the space shuttle. So it has 24 microthrusters, okay? We can see examples of that in the movies in Gravity as well. When you can see here, George Clooney, basically, after an espresso or something probably stronger, because he seems to be a little bit random in his moves there, I don't know what he took. Okay? But the idea is that he's activating his thrusters to move around in different orbits. Or in the Martian again, the brave commander of the Hermes going in rescue mission of Matt Damon, again activating the different thrusters, where we even get a close-up of some of the devices in the backpack that are used to that end. Okay? Good. Remember, I'm from academia, so I can understand even if it's Saturday morning, I have to put you an exam. Okay? I have to put you an exam. So we'll see, just to close, 2 times, one scene. This is from the Bible, Star Wars, from the Empire Strikes Back. The idea is that you have a 1-minute shot and you have to identify as much as you can the number of things that probably doesn't make a lot of sense. So let's go for that.
Choice set 271.
What are you doing? You're not actually going into an asteroid field.
They'd be crazy to follow us, wouldn't they?
Sir, the possibility of successfully navigating an asteroid field is approximately 3,720 to 1.
Never tell me the odds.
I take it back. We're going to get pulverized if we stay out here much longer.
You can argue with that.
Pulverized?
I'm going in closer to one of the big ones.
Closer?
That looks pretty good.
That looks pretty good.
Yeah. We'll do nice.
Excuse me, man, but where are we going?
Okay, so that was for just to put you in context. Now it's time to identify the mistakes.
Look! Ah, crap, there's 2 more of them dead ahead. It's all right, I think I can outmaneuver them.
What are you doing? You're not actually going into an asteroid field.
Sir, the odds of successfully navigating an asteroid field are 2 to 1.
Never tell me the... Oh, actually, that's not bad. Yeah, no, let's keep going. Look, we got 4 or 5 of the main characters on this ship. I think we'll be fine. All right, let's park right there in that cave.
What are you doing? You can't park there.
You're not handicapped.
I have vertigo. It's a real medical condition.
I'm just going on record as saying I'm not comfortable with this.
Good, so I hope you identify many mistakes. Just let me finish by saying there is a tendency in science fiction to think that the universe has been designed to our use, and the size of the universe is the proper one for us to just go there and enjoy and visit every single corner of the universe. Well, just our galaxy is big enough to avoid that, having an an interstellar conflict with a planet somewhere in the other side of the galaxy will be a problem. I don't have time to elaborate on that. And just let me finish by saying that probably the biggest mistake appears in Independence Day. In terms of distances, okay, just a slide before people get nervous, is when Will Smith's girlfriend gets upset after watching some of these huge, space crafts in the different cities, and she says, "Well, these are a menace." But then Will Smith, who is a smart guy, makes a claim just to justify that this is not true. They say, "Look, I really don't think they flew 90 billion light years to come down here and start a fight." Okay, well. A few moments later, this is what happens, okay? So yes, apparently coming from very far away is not a reason why you don't need to start a fight, okay? So 2 questions, and with that I finish. First one is, okay, there is no possibility of communication with these aliens. We don't know actually which language they talk about. We don't know anything about them. So how Will Smith knows by heart that they are coming from 90 billion light years away, okay? My only explanation is probably for the plate somewhere on the spaceship, okay? Which I didn't see, but that's the only way to identify where they're coming from, okay? So maybe that explains where the origin. And second, wow, 90 billion light years seems pretty far away, right? Actually, this is beyond any possibility of observable universe. So it's beyond the observable universe, meaning that they come to the Earth, which is outside of their observable universe as well. So how they know we are here, first. Second, the travel from that distance begins before the Earth was born, actually, okay? So the Earth is relatively recent in astronomical standards. So how do they know? This is incredible. They have escaped millions and billions and trillions of galaxies, okay, just to come to Earth. Come on, this puts Earth at all the main travel guides at the universe scale. So I can only say I would like to thank the aliens for coming. It's a pleasure. They took such an effort, and I would like to thank you for your patience and your attention.